Humans tear apart gold mines for luxury, but they excavate copper mines to support the entire modern world. Every day, hundreds of thousands of tons of copper are woven into the lifeblood of civilization. From smartphones and electric vehicles to the vast power grids that keep modern cities running. Yet producing just 1 ton of pure copper requires mining companies to excavate and process hundreds of tons of rock, from deep beneath the Earth's surface. Join us as we travel to one of the largest copper mines on Earth. Copper is largely formed from the cores of dying giant stars, before supernova explosions scattered it into the Earth's interior billions of years ago. Copper in nature is almost non-existent as a pure metal. Instead, it is mostly locked within ores, such as oxide ore and sulfide ore.
And the copper content is only about 1%, meaning that for every ton of mined rock, only 10 kilograms of copper is obtained.
An estimated 26 million tons of pure copper are mined annually. But this thirst shows no sign of easing, as the explosion of the semiconductor industry and AI supercomputers has turned copper into the red gold of the new era. So how do these virtually worthless blocks of rock buried underground transform into pure copper? It all began at Escondida in Chile, the world's largest copper mine. Seen from above, it resembles a giant gash on the Earth's surface. The open pit mines up to 600 meters deep, taller than skyscrapers, stretching 3.5 kilometers long and 1.5 kilometers wide, create a mining operation on a scale far exceeding anything man has ever built. The stubborn rock formations could not be excavated intact. Therefore, the first step was to use controlled blasting to transform an entire mountainside into thousands of tons of loose ore. Now, massive drilling rigs go to work, drilling enormous blast holes in preparation for the next explosion. They move across the mining bench, drilling hundreds of holes into the rock. Each hole typically measures between 10 and 16 inches in diameter and extends from around 30 to more than 70 feet deep, depending on the hardness of the rock and the location of the ore body beneath the surface. Immediately after the drills are pulled up, the mining area enters one of its most crucial stages, preparing the blasting site. Hundreds of boreholes are connected by a network of interwoven electronic detonating wires, like a spider web, spread across the surface of the mining layer. Then, industrial explosives are loaded in quantities calculated beforehand by engineers. They often use a combination of TNT and emulsion explosives to create enough energy to break up hard rock formations deep underground. After completion, the borehole openings are sealed with specialized material to keep the blast energy concentrated underground, instead of escaping back to the surface. Everything is designed with the same goal. Not to create the biggest explosion, but to create the most effective explosion to facilitate the mining process. Once the area has been completely evacuated, the electronic blasting system is triggered from a safe distance. In just a few seconds, hundreds of thousands, or even more than 1 million tons of rock can be fractured in a single blast. From above, the scene looks like a miniature earthquake. Massive clouds of dust rise hundreds of feet into the air. And behind that wall of dust, the copper-bearing ore. Locked deep underground for millions of years, has finally been set free. As the dust settled, a series of massive hydraulic excavators began to move into the recently excavated area. These machines weighed hundreds of tons, with buckets large enough to lift an amount of earth and rock equivalent to the weight of a car in a single pass. Each bucket of ore was dumped into specialized mining trucks waiting below. Some of the largest models used in copper mines can be taller than 2 stories and carry between 200 and over 400 tons of earth and rock in a single trip. Their tires alone are taller than an adult, and each costs tens of thousands of dollars. Once loaded, the convoy began its journey.
transporting the ore along the enormous spiral roads within the mine.
Each trip could extend for tens of kilometers from the bottom of the excavation pit to the processing areas above. At large quarries like Escondida, hundreds of trucks operate continuously day and night, forming a massive transportation system capable of moving hundreds of thousands of tons of earth and rock every day. Managing a fleet of this size requires a sophisticated dispatch system. Every truck continuously reports its position and operating status through GPS and onboard monitoring systems, allowing controllers to track equipment and personnel across the mine in real time. From a central operations center, software and dispatchers coordinate routes, assign tasks, and optimize traffic flow to keep production moving.
The massive haul trucks have two different destinations. Depending on the copper content, the ore is divided into two categories: high-grade ore and low-grade ore.
These two types of ore have completely different processing procedures. Low-grade ore is transported to leach pads,
where millions of tons of ore are stacked into enormous heaps.
A network of pipes then continuously sprays a dilute sulfuric acid solution over the surface of the ore.
This solution slowly percolates through the layers of rock, dissolving the remaining copper trapped inside. The process is extremely slow.
As the solution reaches the bottom of the heap, it now contains a large amount of dissolved copper ions. This copper-rich solution is collected through a system of drainage pipes and specialized holding ponds. Interestingly, this copper-bearing solution is blue in color,
even though pure copper is orange. If anyone can explain why, let me know in the comments. The solution is then sent
to a recovery plant, where the copper is extracted and processed into highly pure copper cathode sheets. Stations. But when it comes to high-grade copper ore, things become much more complex. After leaving the mining area,
Every day, hundreds of thousands of tons of material move through this system,
which operates almost continuously around the clock. The entire operation is designed to keep a steady flow of ore, moving from the mine to the next stage of processing with as little interruption as possible. Inside the processing plant, the ore continues into massive sag mills and ball mills.
These machines can measure dozens of feet in diameter and contain hundreds of tons of steel balls.
As they rotate continuously, the steel balls strike the ore millions of times, gradually grinding it into extremely fine particles. After hours of processing, what was once solid rock has been transformed into a fine powder. This powdered ore is then mixed with water and specialized reagents to create a slurry. From the mixing tanks, the slurry of the entire process, flotation. Here, air is continuously injected into large flotation cells, creating millions of tiny bubbles. Special chemicals cause the copper-bearing mineral particles to attach themselves to the surface of these bubbles. As the bubbles rise to the top, they carry the copper minerals with them, forming a thick layer of froth on the surface. The copper-rich foam is then collected and transported to massive concentrating tanks, where most of the water is separated to form copper concentrate. However, the copper concentrate still contains significant amounts of sulfur, iron, and other impurities. To remove them, the concentrate is inside the smelting furnaces. Temperatures can exceed 1200 degrees Celsius. Here, a series of chemical reactions takes place, removing most of the sulfur and other unwanted elements from the material. After several stages of high-temperature processing, what remains is molten copper,
with a purity of about 98 to 99%, commonly known as blister copper.
The molten copper is then cast into massive metal plates called anodes, each weighing hundreds of kilograms. These copper plates are quickly cooled down with cold water before being transferred to the electrolysis process. These anodes are suspended in electrolytic tanks that can stretch for dozens of meters and are filled with a solution of copper sulfate and sulfuric acid.
When an electric current is passed through the system, Copper atoms gradually dissolve from the anodes, travel through the solution, and over the course of several days, layer after layer of pure copper builds up on the cathodes.
While most of the remaining impurities are either left behind in the anodes or settle to the bottom of the tanks.
Pure copper cathode plates are removed from the tank and transferred to the product finishing area.
Here, mechanical arms and automated systems lift, move, and stack each copper plate according to pre-programmed specifications. Then, dozens of cathode plates are stacked together into large bundles, forming heavy copper bales weighing tons, ready for shipment.
However, the journey of copper doesn't end there. At metalworking plants, copper cathode plates
are fed into furnaces where they melt at temperatures exceeding 1,000 degrees Celsius to form molten copper.
The molten metal is then cast into long ingots or bars before continuing through a series of specialized rolling and drawing machines.
With each stage, the diameter of the copper wire is gradually reduced, but its length increases significantly,
while its purity and conductivity remain unchanged. Finally, the copper wire is wound into enormous coils and transported to factories that produce electrical cables,
motors, transformers, and countless other devices that power the modern world.
To obtain 1 kilogram of pure copper for the modern world, the environment is sacrificing 300 kilograms of toxic slag waste. But even more frightening is what's invisible to the naked eye. Every time it rains, highly toxic heavy metals like arsenic, lead, and cadmium from the waste dumps are washed away,
seeping deep into the soil and killing groundwater sources. These enormous mountains of slag
are essentially ticking time bombs, silently destroying the ecosystem day by day.